Welcome to the deep dive.
Hello.
This is where we take a stack of sources, dig right in, and pull out the good stuff, the key insight, the surprising bits, so you can get up to speed quickly.
Yeah, think of it as your fast track through complex material. We sift through it so you don't have to.
Exactly. And today, we're diving into something pretty specific, actually sparked by a document one of you shared with us.
hmm
It's all about tackling a particular mathematical problem.
hmm
Our mission, basically, is to figure out how a specific method, the one outlined in this source, is used to solve what looks like a really, really tough equation.
Right. And the equation in question is a polynomial of degree 7.
Degree 7. Okay. So straight away, that means we're hunting for 7 solutions, 7 roots for x.
Exactly. And, finding roots for a general seventh degree polynomial, that's notoriously hard. There's no simple plug and chug formula like the quadratic one we all learned.
Right. No easy way out, usually. And this specific polynomial, let me read it from the source. It's px equals no plus 1 plus 1 through oman. Juvan pia plus on.
Wow. Yeah, just listing those coefficients. It sounds pretty daunting.
It really does.
But the interesting thing is, the document you shared puts forward a specific method, and it claims this method can crack this specific polynomial.
Okay, so let's get into how the source says this method works. It seems to start by representing the polynomial differently. It talks about the original coefficients being related to these new values called O and O.
That's right. It's sort of like the first step in translating the problem. You take the polynomial as given, and you re-express its structure using these tar values.
Okay.
And the source actually gives the specific numbers for this polynomial. It says Onia's is 14, Odez 84 is 281.
Mm-hmm.
Sad. Milor is minus 3128 or is minus 4680 or is 23328. And finally, Ardos is 37776.
Right. So these numbers come directly from those coefficients I read out earlier.
Precisely. They are derived from them according to the method's first step.
Got it. So original polynomial, translate coefficients into these two values. What's the source say happens next?
Okay, so this is where let's say the main engine of this method comes in according to the document. It uses something called the discriminant formula of Mourad, Sultan, Ezouidi, Hism.
Okay, that's a mouthful.
It is, but let's not get too bogged down in the formula itself right now. The key thing is what the source does with it.
Right, so what does it do?
It takes those Bordier values we just listed.
The 14, 84, 281, etc.
Exactly. And it applies this discriminant formula through a series of calculations. The source shows these calculations for different steps, different k values, to get another set of values. These are called war, which then relate to values called war.
Okay, so will values go in, this formula churns, and Erdős values come out.
Basically, yes. And this is where, for this specific polynomial, the source reveals something quite remarkable about these resulting woe values.
What's so remarkable?
Well, it's how incredibly simple most of them turn out to be. The source calculates them from 0 up to 6 and reports O 0, then skips S2 for a moment, O OU, and O W and 0.
Wait, hang on. So almost all of them are just 0.
Exactly. 6 out of the 7 main values associated with the polynomial terms from XEO down to the constant term. They're all 0.
Wow. Okay. That seems unlikely or very specific to this problem.
It's definitely very specific. The document notes 2 exceptions. There is a structural value, which equals 1, but that doesn't show up as a coefficient in the standard form. And the really crucial one is not 0. It equals 343.
343. Okay. So lots of zeros and one non-zero value, 343 for...
Precisely. And this pattern, mostly zeros, is, according to the source, the absolute key. It's what makes this specific polynomial solvable by this method.
Right. So how do these O values, especially all those zeros in the 343, help solve the actual polynomial px?
Well, the source shows that the polynomial px can also be written using these O values as coefficients. The general form is shown as px x x x x. Okay, that looks like a standard polynomial form, but now we plug in the values we just found.
Exactly. Watch what happens. Px becomes xx minus 0 times xx plus 0 times xs plus 0 times x plus 9 times x minus 0 times x minus 0 all equals 0.
Oh, wow. So all those terms just disappear.
Right. The equation simplifies massively. As the source shows, it just boils down to x 343x x 0.
That's amazing. That huge beast of a polynomial we started with just collapses down to 2 terms. Because of that very specific pattern of zeros in the O values, yes, This is the power the source claims for this method when applied to a polynomial with these hidden properties.
So x out of 340 away equals 0. That looks much more manageable. How does the source solve this simplified version?
It factors it. You can see there's a common factor of x.
Yeah, of course.
Yeah.
So you pull out xazo, leaving xf of 343 inside the parentheses. So it's xazo times x at 343 equals 0.
Exactly. So according to the source, this complicated looking degree 7 polynomial actually factors into the product of these two simpler bits, xa's and xlo 343.
Okay, and solving px now means either the first bit is 0 or the second bit is 0.
Correct. So we need to solve xo 0 and we need to solve xo 343 equals 0.
Right, let's take the first one. Following the source, xlo was, well, that's pretty straightforward. The only number that works is x equals 0.
And because it's x to the power of 4, the source indicates this solution, x0, has a multiplicity of 4 at this intermediate stage. It writes them as xk for k00, 1, 2, 3 are all 0.
Okay, but these are the x values. How do they become the actual roots of the original polynomial? The source mentions another step, right?
Yes, there's a final transformation. The source gives a formula to convert these intermediate x values into the actual roots, which it calls alpha. That formula is xk plus xk7.
Okay, so it uses that TOA value we found way back at the start,
Yeah,
which was 14.
correct. And the 7 is the degree of the original polynomial.
So for our xk0 values, we plug that into the formula. x14 plus 0, 7.
Which is?
14, 7 to 2.
Right. So according to the source, this means 4 of the 7 roots of that big original polynomial are actually just the number 2.
4 roots equal to 2.
Yeah.
Okay, what about the other part of the factored equation?
That was xt 343 equals 0, or, x equals 343.
Right. We need to find the numbers whose cube is 3 and 43. I know 7 times 7 is 49, and 49 times 7 is, let's see, 50 times 7 is 350 minus 7.
Yeah,
343. So x7 is one root.
It is. That's the real root. But remember, it's a cubic equation, x cubed. So there should be 3 roots in total, including complex ones.
Complex roots. Right. How does the source find those?
It uses the standard way to find the cube roots of a number using complex exponentials. The source writes the solutions for x as xk is cube root of 343, which is 7 times e to the power of 2 times k times I times pi divided by 3. So xk will 7e to x 3 for k equals 0, 1, and 2.
Okay. Unpack that a bit. For k0.
For k0, the exponent is 0.e degrees is 1. So x0 is 0, 1, 1, and 2, 7. That's the real root we found.
Got it. For k1?
For k1, you get x0 is 7e2i3. That's a complex number.
And k2?
K2, you get x0, 7e4i3. Another complex number. These 3 values, 7e2i3 and 7e4i3, are the 3 cube roots of 343.
Okay, so those are the 3 x values from the second part. And now we use that same transformation formula again. Ag plus xk7.
Exactly the same one. We plug in I14 in each of these 3 xk values.
So IK14 plus 7e2 IK37.
Which simplifies quite nicely, doesn't it? You can divide both terms in the numerator by 7.
Oh, right. So 147 is 2, and 7e2 IK37 is just e2 I3. So the formula becomes IK2 plus e2 IK3.
And we calculate this for k0, 1, and 2 to get the remaining 3 roots of the original polynomial.
Okay. For k0, I0 is 2 plus e agrees 2 plus 1 will 3.
There's 1 root.
For k1, a is 2 plus e2 I3. That's a complex root.
The second complex root.
And for k2, a0 is 2 plus e4 I3. The third complex root.
And those are the remaining 3 roots.
So let's just recap what the source showed us. We started with this really long, complicated degree 7 polynomial.
Looked almost impossible to solve directly.
Right. But the source applied this specific method, translated coefficients to Udiro values, used this special discriminant formula to get color ray views, found almost all of them were 0, except 3, 4, 2, I4, 3.
That was the critical step, that pattern of zeros.
And because of that pattern, the polynomial simplified dramatically to xe343 euros equals 0.
Which then factored into xe343 equals 0.
Making it easy to solve. The x0 part gave 4 roots of x zeros in the intermediate step, which transformed into 4 roots of alpha 2 for the original polynomial.
Using the formula xq I14 plus xk7.
And the xsoc equal 343 part gave 3 roots for x, 1 real, 7, and 2 complex, which transformed using the same formula into the roots alpha and the 2 complex ones, 2 plus e2 pi 3 and 2 plus e4 I3.
So in total, 4 roots are 2, 1 root is 3, and 2 are complex conjugates. That's the 7 roots accounted for.
It's actually quite elegant how the specific numbers in this polynomial worked so perfectly with the method described in the source to allow this clean factorization and solution.
It really shows how sometimes The apparent complexity on the surface might hide a much simpler structure if you have the right tool or perspective to reveal it. The method basically found a way to exploit the specific relationships between these coefficients.
Yeah, it really makes you think. Which leads us nicely to a final thought for you, the listener, to chew on. How often do you think the specific details of a problem like these coefficients hold the key to unlocking it, hiding a simpler path that only a very specific method or formula can find?
Right. What other areas, maybe completely outside mathematics, might have complex challenges that are just waiting for someone to find that right perspective, that specific formula or approach that suddenly makes everything click and simplifies the whole thing? Something to ponder.